Thank you for joining us today, and it's great to be here at Databricks AI Summit, and I hope everyone is having a wonderful time. And my name is Bharat Gamani. I'm lead security data engineer at Adobe. Over the past few years, I've been involved in designing and building cybersecurity-focused advanced analytical data lake on Databricks using AWS. And join me today is Andrew from Antimatter. Andrew?
Thanks, Bharat. Hey, everyone. Andrew, I'm the CEO and co-founder of Antimatter. We're a cybersecurity startup. A lot of our team is here. You guys can ask us questions afterwards. We help you build security lakehouses on top of Databricks. I'm excited to show you more of what we do in just a little bit. Back to you, Bharat.
Thank you. So this is our agenda for today's session. So we'll discuss what Adobe's cybersecurity data platform is, why we have both SIEM and data platform, and advantages of the data platform. And we'll also look at data standardization at scale, challenges with that, and what OCSF is, and how OCSF can solve some of these challenges. And finally, we'll look at Antimatter Security Lakehouse and the demo, and we'll take questions at the end. Before we dive deep, curious how many of you are here in cybersecurity space? Wow, great. At Adobe, we face similar challenge as many of you do, how to turn massive volumes of telemetry logs into timely, actionable insights. We have built our security data platform to tackle exactly this, enabling us to ingest and analyze security logs at petabyte scale and respond faster with analytics. But the real opportunity with SDP is this. It gives us power to shift left from reactive state to proactive state by unlocking patterns, detecting threats earlier, and enabling smarter decisions. And onboarding security data alone is not our primary goal. Meeting our stakeholder needs is. Across Adobe, different stakeholders rely on this data for a variety of purposes. SOC, which is front line of defense, they are responsible for monitoring, reacting to the security alerts. They need access to real-time alerts and correlation and case management workflows. And threat intelligence and threat hunting team focus on emerging threats, adversary behavior, and new attack patterns. They need access to the raw logs and ML models to fight these adversaries. And incident response team handles the investigation, containment, and recovery of the security incidents. They need access to the historic data as well as ability to process these historic logs efficiently, and they need access to this long-term data storage. And enterprise security team ensures secure access, authentication, and security access controls of enterprise applications. They need cross-platform data correlation and security tool administration. Each group has their unique requirements, but they all share one common dependency, which is high-quality, normalized security logs at scale. That's where our Lakehouse model shines. When we mapped who depends on what, we have identified that traditional SIEM and our security data platform weren't competing. They are complementary to each other. SIEMs gives us mature workflows, correlation engines, and case management workflows, but scale, flexibility, and innovation, SDP has been irreplaceable for us. With OCSF-aligned data pipelines, we are providing structured, variable data for threat detection models, advanced analytics, and ML. Yes, there is. Going to the next, why we need both SIEM and SDP? That's the important question asked by many. SIEMs give us mature workflows and case management engine, but cost, lack of flexibility in storing for long-term, and long-term flexibility of the logs is a drawback for us. On the other hand, SDP gives us cost-efficient, decoupled storage, which supports petabyte scale logs and advanced ML and analytics. It requires some expertise, but it's also what opening doors for us for advanced analytics and ML. That's the core of Adobe's approach, using strength of both platforms connected through clean, normalized OCSF data. And with Databricks, we are accelerating towards advanced, intelligent, and adaptive security operations. Let's look at how the adoption and impact actually looks like. Currently, we are supporting over 300 users across 20 different teams from product and security, and we are currently hosting around 21 petabytes of security logs. We run around 14,000 queries per day. Even though the usage is growing significantly, our performance remains solid. This is due to our pre-processing and optimization techniques we have done in ELT layer. And our average daily query success rate is around 97%, which is a key indicator of the overall platform performance and health. These metrics shows the overall adoption rate and the strong platform efficiency, and we are continuously growing our platform. Let's look at how this all tied together. So this is heart of our functional workflow. Starting from the left, we are collecting data from different sources via Cribble, which is our data collection tool. Cribble sends log to different destinations, in this case, both SIEM and our data platform. In the data platform, we collect the data, process the data, and make it available for end users. We have different user personas, data analysts, engineers, and data scientists. Each use this data differently. And analysts rely on this data for ad hoc analysis and dashboarding and reporting, whereas engineers and data scientists run complex ML workloads and Spark jobs. We also push the results from our ML models back to SIEM and SOAR for real-time alerting. So everything connected here is connected through common data governance model using Unity Catalog and common schema framework, which is OCSF. The glue behind this is strong technical foundation anchored by the Databricks. You may be seeing all of the Databricks services here, but yes, we are using all of them. We are collecting logs from 50+ different sources, from APIs, files, databases, log forwarders, and Splunk. And Cribble collects these logs and pushes the data to our S3 buckets. And in our data platform, we run batch and streaming data pipelines, majorly using autoloader to ingest data through our Medallion architecture. All these workflows are orchestrated using Databricks workflows deployed via Databricks asset bundles. And our analysts use our serverless SQL warehouse capabilities to run ad hoc queries, and our engineers run Spark jobs using classic compute as well as serverless compute. We are relying on Mosaic AI, vector database, and vector search for our AI use cases, and we follow MLOps for model registry and model serving. And Databricks Assistant and Genie has been invaluable for us in answering questions using natural language and fixing our code in place. Overall, this is our Lakehouse platform built using Databricks. I haven't gone deep into the architecture and infrastructure details. Please feel free to connect me after the session if you'd like to learn more details. Now let's look at some of these things in action. We have built anomaly detection model to identify unusual login behaviors. So this is autoencoder-based model which learns typical user login behavior and flags deviation due to credential misuse or lateral movement. This has proven to be effective in identifying the real threats earlier without overwhelming analysts with too many false positives. Now let's shift our gears towards an AI solution we have built. So this is a semantic search application we have built on top of the data lake. What this does is it helps analysts understand the command line activity by providing them historic command lines and explaining them the behavior and providing them the recommendation. This has significantly reduced the overall investigation time and boosted the analyst efficiency by turning noisy logs into actionable insights. These are just a couple of examples, but similarly, we have built numerous use cases on top of the data platform and gaining full value out of it. Let's look at the overall business value of the data platform. At its core, SDP is about stronger, faster detections at lower cost. We have consolidated fragments of data into a single source of truth. We have improved the data quality and performance, and we have enabled self-serve analytics. We have also included advanced analytics and MLs backed by data governance and encryption standards. We have continuously improving our unit costs a must as we are scaling. Overall, this shows about how strong and efficient our security data platform is and how effectively our users are using the platform for. So far, I've been discussing about what data platform is and what are the benefits. Let's look at one of the major challenges of the data platform, which is data normalization at scale. As we ingest petabytes of security logs into the system, we ingest logs from variety of the vendors, and each vendor sends the logs in different formats. As an analyst, it becomes difficult to write queries differently for each vendor. It hampers the analyst efficiency and the time to write the detection and time to find the evidence. So having the data standardization in data lake helps in reducing the ingestion complexity, speeding up the total value, and enhances the analyst and detection accuracy. Andrew will talk more about OCSF and how OCSF can solve some of these challenges. Andrew?
Thanks, Brett. How many of you all have heard of the OCSF framework? Show of hands. Okay, majority of the audience. All right, that's great. That's great. So this may or may not be new for folks. OCSF was a framework that AWS was the primary sponsor of back in 2022. And really the vision of this was, could we take an open source approach, a consortium-driven approach to coming up with a normalized format for security data? So it's essentially a specification that has a bunch of tables, a bunch of columns that are all predefined, and essentially you're mapping security data from vendor logs to this normalized standardized format with the promise that if you do that, you can write your queries once and have them run across all of your security data, breaking down essentially silos that you might otherwise have. So that's the vision of OCSF. I'm gonna walk through an example of actually taking some abridged data and normalizing it to OCSF and kind of talk through some of the pros and cons. What are the challenges with this? When is it useful? When isn't it? We'll do that in a second. So to do this, I'm going to start with an example of WAF data, web application firewall data, from Akamai and AWS. This is actually something we worked on together with Adobe, so it's quite representative. Very common, as you all probably know, web application firewalls protect your web apps from things like SQL injection attacks, for example. And they generate logs with attempted attacks, detected attacks. They'll have HTTP activity, very interesting data to potentially correlate, understand who's attacking your system, what are they trying to do, et cetera. So one of the challenges, of course, if you have multiple WAFs, because you maybe are using multiple clouds, or maybe you have disparate products, how do you analyze that data in a standard way instead of having to basically treat it as vendor A and vendor B having completely separate pipelines or query patterns? So with that setup, what we're going to do here is follow a medallion architecture for transforming this data. We're going to start with raw data, which looks like JSON blobs, in a bronze table. You can imagine we maybe used an autoloader to pull that in from S3 buckets, or maybe we have the tool automatically push that data directly to some kind of cloud object storage. Then we're going to take the data and transform it into a silver table where we're essentially pulling out columns, but still keeping it in largely a vendor-specific format. We'll show you that in a minute. And then finally, we'll take it all the way through to a gold format, which will conform to the OCSF standard. And you can see what that looks like in a minute. So to jump right in, what I'm showing you here is a abridged example of the kind of JSON blob that you would get out of a WAF. On the left is AWS, on the right is Akamai. If we were to zoom out, essentially what these bronze tables look like is thousands and thousands of rows of JSON objects. Pretty hard to work with. If you were to try to work with this data directly, maybe you're doing a regex, maybe you're trying to apply some kind of structure to this. Quite challenging, different for every vendor you're working with. And you can see that if you zoom in a little bit here, so kind of a peek at what this data looks like. You can see in both cases, it's pretty simple, it's pretty similar. You're seeing HTTP requests, you see the host, you see a path, you see user agent in both cases, but the formats are different. So quite clear why that would be annoying to deal with. Things like timestamps, one's in milliseconds, one's in seconds, those kind of problems. Again, simplified example. In reality, these JSON blobs are 10 times as long as what I'm showing you here, so it's sort of death by 1,000 cuts in terms of dealing with this data. So the first thing we'll do with this is transform it to what we call a silver table. And so all I'm doing here is applying some structure to the data. So take the JSON blob and kind of explode it out into columns. Here, let's say we pull out the client IP, we pull out the headers, and the key here is we're applying structure. So headers, we're using the fact that we know that's an array of name-value pairs, and by doing that, it's much more efficient to query that kind of a column than it is to query something that's just a unknown structured JSON object. HTTP request, et cetera. So these column names are vendor specific, as you'll see when I jump to Akamai, similar data, different names, slightly different format. Here we have response headers and request headers. We have IP as well, we have time as well. So you could write queries against this, you could write detections against this. Many people do, that's quite common, but what you don't get is this consistent approach across all of your vendor data. So that's the promise of OCSF. And so this is a piece of what OCSF looks like. So with OCSF, you have a prescribed set of tables that you can map your data into, about 100 or so of them. So the first thing you're doing is deciding what event type you're even looking at. Here, HTTP activity is one of the table names, one of the classes in OCSF. So we've decided that all of this data fits into HTTP activity. That's actually non-obvious. Mapping to OCSF is a little bit more of an art than a science. There's often many places where you might put any given piece of data. And that's one of the challenges with it, is then as a user of this, do you immediately know where to look to find your data? So in this case, pretty simple example. We're saying it all goes into HTTP activity. And then you have easily 100 different columns that you can map that data into. I'm showing you 5 of them here. So timestamp, metadata showing which one came from Akamai, which one came from AWS, source endpoint, where did the request come from, the actual request. And these formats, these little JSON blobs here are now in a prescribed format. So you know IP will always be inside of source endpoint. So what you're getting there is something that's easy, consistent to query, but what you're losing potentially is not all of your data can necessarily easily be mapped in this way, and there's a long tail of fields that you may or may not choose to map, and that may go in one of many different places inside the OCSF spec. So that's kind of the trade-off. This is, of course, a simple example. If I sort of actually show you some real OCSF mapping that we've done, take AWS CloudTrail, you're dealing with over 430 event types. So those event types don't all go into the same table. So the first thing you're dealing with is, what event do I actually see here? Which of the OCSF tables does it go into? Then you see that each of those event types, I'm showing them in columns here, are event types. And then in the rows, you're seeing different fields. So the schemas are inconsistent across the event types. And of course, there's no documentation for any of this. So you're essentially looking for examples of, what does each event look like? What kind of fields can I pull out of that? Where do I map those into OCSF? And that's some of the challenge of doing this for real data. So if we zoom out, when is this actually useful? What can we do with OCSF? What we found is that it's best applied for your most important fields. Because essentially, the challenges here are, as I mentioned, the vendors often don't have documentation for their logs. The schemas for the logs often change. There's a long tail of data in different log events, and these events are not consistent. And then you might put this data in one of many places in OCSF. So with those challenges, how do we actually use this thing, and when is it useful? Well, what we've found collectively is that this is most useful if you either have lots of vendors for a common event type, and you want to analyze those in a common way. So my example with WAF data is pretty common. You might do this for identity data if you have like Entra and Okta at the same time, for example, or other identity providers that you're using. It's also quite useful when you have data sets that you need to frequently join, because obviously you need to join them on some column, and so having that in a standard column name and a standard column format where you know your joins will succeed makes that a lot easier. That's what we're finding. And you can do that by mapping a subset of the fields. So you don't necessarily have to do the long tail and treat OCSF as the sort of definitive format where you've mapped everything to it, you can treat it as something where you've gotten kind of a majority or the most important parts of your data. And more generally, we see there being a bit of a trade-off here between how much effort you're putting into the data normalization process up front and then how easy it is for a user to query at the end of the day. So you can also work backwards from knowing what your use case is, what your users are actually going to want to access, and make sure that that's where you're focusing your mapping effort. If the users don't know where to find the data, there's not much use in having spent a lot of energy trying to map it in. So that's a high level of what we're learning about and seeing about OCSF and working together on this. We'll take some questions on that in the end. But I want to pivot for a second and talk a bit about antimatter and what we're building with the Security Lakehouse. We're lucky to have Adobe as a user of that, and we'll share a little bit of what they've done with the platform where OCSF normalization is a piece of it. So at a high level, I mentioned we're a startup in the security space. We're building a solution that works on top of Databricks, largely motivated by observing that a lot of, largely you folks in the room, a lot of Databricks customers have been DIYing a security lake on top of Databricks, building their own ETL, building their own ingestion pipelines, their own detections, and that's quite time-consuming. It's quite difficult. Not everyone has the in-house expertise to be able to do that, and so what we have is a product that runs within your own Databricks workspace and makes this a lot easier, gives you a kind of user interface on top of it all, does a lot of the heavy lifting of managing data pipelines for you. I'll show you a quick demo of that in a second. This is live in a beta format right now. As I mentioned, Adobe's one of the early users. So first of all, what is a security data lake? What would you even want to do with such a thing? And there's a wide range of use cases here. We're focused on kind of this dominant row down the middle. So what you might want to do is first ingest a bunch of data. How do I get my log data into a security lake? Then normalize it. Can I get it to OCSF or at least get it to a silver table? Might want to enrich it or apply aggregations on top of that data so that I merge it with some data sets I already have. Then I want to run detections on top of it so I can understand if someone's attacking my system or if someone's maybe an insider threat or other types of attacks that you might have. Be alerted if any of those detections go off. That's what we see as the most common critical path that folks go down, but there's other things you may want to do. You may want to investigate those alerts. You may want to do threat hunting and actually look for vulnerabilities or attacks that you might not know about yet. And then there's case management and actually responding to these attacks. And there's Databricks customers doing all of these parts within Databricks. We're working to kind of expand out what we can offer to make that a lot easier. And more generally, if we kind of zoom out and look at the market at large, we see a big trend happening and a big change happening where folks are moving from monolithic SIEMs that are these special purpose, long-standing applications that increasingly have scaling bottlenecks, they have large costs, and limited flexibility. You heard Brat speak about this at the beginning for why Adobe has a security data platform to begin with instead of just a SIEM. And so the future, as we see it, is a move to these more modern cloud-native architecture built on top of Databricks, where you have much greater scalability. You can easily go to terabyte scale. You have Spark under the hood for really great performance. You have much more cost efficiency. And on top of that, you're getting the latest AI, ML advancements. Because at the end of the day, we see security data analytics really as just a big data problem. And therefore, a platform like Databricks is actually extremely well suited for it. The only thing that's missing is the interface to really make that a lot easier to use as security experts here. Essentially, how do we adapt from a data science perspective to a security perspective? So that's what we're building. And let me jump in and give you a quick demo of the solution. So this is the antimatter security lakehouse. I'm going to show you just a couple pieces of it and kind of a sneak peek at this. Happy to answer questions on it afterwards or find me after the talk. So first thing I'm showing you here, as I mentioned, that kind of user journey, first thing you want to do is load data into your security data lake. How do you do that? We have the idea of configuring data sources here, where there's a lot of pre-built data parsers, and each one of these is able to take data that you have, for example, in a cloud object store. Let's say I have my Cloudflare WAF data in an S3 bucket. I want to run a pipeline that's going to take that data in, it's going to parse it into a silver table with columns, it's going to transform it into a OCSF normalized gold table, but I don't want to write that code myself. I don't want to manage that pipeline, see if it's still running, debug, be alerted if there's errors, et cetera. We handle that for you, so you can go in and add that data source here, and then what happens behind the scenes is this actually runs a job directly within your Databricks workspace. So you own the data stays in your workspace, the job is running in your workspace, none of that's actually going to antimatter servers, but it's being managed on your behalf. So you don't have to deal with, what if this fails, or how is this actually running behind the scenes. We also let you do a lot of customization. I won't go into it here, but you can actually customize how that mapping works. You can do that either as SQL expressions or as code. So there's a lot of actual flexibility there. There's also a lot of flexibility around how those jobs run. Are you trying to optimize for mean time to detect and you want this to run continuously? Or do you want to optimize for cost? Maybe you run this on a schedule at some interval. That's all possible under the hood. Once you've got your data sources created, you can see I've got some data coming in here. The next thing you want to do is create detection rules. And actually, maybe just before I go there, I'll show you what that data actually looks like when it's come in. So I can go into my Databricks catalog here. Let's see, maybe that's slow. So if I go into my staging environment that I'm in and go to my gold table, so I'll actually see all of the OCSF tables in here. And if I scroll down to HTTP activity, these are the actual column names as per the OCSF spec. And I can go and see some sample data that antimatter is running the pipeline to actually load in for me. And so none of this is locked down in any way. You own this data. You can build anything on top of this if you want to go and run your own job that then takes this gold data and runs with it, does AI/ML, does autoencoders, et cetera. You're able to do that. So once you have your data in the system, the next thing you want to do is run detections. We have a framework for that as well. So in here, you can create detections, which in our parlance are essentially SQL expressions. They can be streaming or they can be batch. And essentially all new data coming in is checked against your detections. You can do joins there. You can do enrichments as well. So anytime one of your detections fires, you actually get an alert in the system. And that's the last part I'll show you here. So within the Explorer, we have a concept of notables, where anytime a detection goes off, you're notified of that. So for example, here I have user Alan has multiple failed login attempts. And so this could be something that you assign to an analyst to investigate. Or you can go ahead and actually export this pretty easily to an external tool. Maybe you're using ServiceNow or Jira or Slack or anything else like that as a way of assigning these tickets to your users. So that's a very quick tour of kind of that common path of ingest, normalize, detect, and alert that we support within antimatter. So the promise of what we're doing is largely around four things. First is reducing the cost of running a security lakehouse. We're finding 15 to 16% cost reductions compared to doing this in maybe an incumbent solution, a traditional SIEM, for example. We're seeing better performance, especially at large scale, because this is running Spark under the hood, so readily scalable. It's also much more flexible for advanced analysis. I didn't give you a lot of that in the demo, but you can actually either write code or use Mosaic AI/ML functionality directly in your detections. And then finally, you own all of the data, and you can manage the system it's running entirely within your workspace. So I'll hand it back to Brad here to talk a bit about Adobe's experience with using the Antimatter Security Lakehouse.
Thank you, Andrew. So before we wrap up, I want to touch on our experience using antimatter Lakehouse. At Adobe, we are using antimatter along with Cribble to ingest and normalize security logs into OCSF format. What stood out with antimatter is how flexible and performant the normalization process has been. It made us move things very fast, and we are able to lay the foundation for all our AI and ML use cases. And antimatter is Databricks native and Spark-based, so it integrated smoothly with our existing tech stack and enabled us with performance at scale. While the OCSF is still evolving, we are continuing to explore other tools, and so far, antimatter has been front runner in this space in terms of innovation and flexibility. Antimatter also makes it easy to share, reuse, and collaborate the schemas with a broader community. It closely aligns with Adobe's goal of contributing back to the community as we scale our platform. Thank you all. Thank you for attending, and we'll open up for questions. Thank you.